So stop 42 seconds on responses, and go to names and we're going.
Okay. Hey, does it sound good in the back? All right. Silent. Oh, a little louder. Let's try. How about that? Does that sound good? Same? Okay. I'll try to speak with my big boy voice. We'll see how that goes. Okay, good evening, everyone. Thank you for coming to this talk. I'm Adam Everspaugh. I'm a soon-to-be former PhD student at the University of Wisconsin. By that I mean I hope to be graduating, not that I'm dropping out. I study cloud security and applied cryptography, and I'm here to talk to you today about some fairly exciting new research, some new cryptographic primitives, and a protocol for using them with passwords, which we think is going to really improve the way that passwords are used today. This is work originally presented at Usenix Security back in 2015. This is joint work with two other PhD students, Rahul Chatterjee and Sam Scott. Rahul's at Cornell Tech, Sam Scott's at Royal Holloway in London, and also two professors, Ari Jules and Tom Ristenpart, both of which are in Cornell Tech. Okay, so we use passwords every day. We use these things to authenticate to our devices, and we use these things to access online servers. Sorry, let me do this one more time. Arrangements. 2 displays, and I can see all my notes. All right, and what about now? Now you guys are seeing the secret side. Let's try this way. That's no fun. Now you guys get to see the good stuff. Is that the trick? We'll see. If not, I'll fly with no notes. We'll see how it goes. Okay. Not going to work. We'll do this. We'll do it like this. Okay. So, we use passwords every day. We use these things to log on to our devices and our online services. But the way we're using these passwords, the way we're storing these passwords is fundamentally broken. And the reason for that is password databases get stolen. And when they get stolen, it's too easy to crack these passwords. So what I hope to present to you today is a new direction. So a new architecture for protecting passwords. Something built around a cryptographic pseudorandom function provided as a service. And this is going to not only prevent offline attacks, but this is going to enable people who use passwords to be able to detect online attacks and do something about them. So they can rotate keys and they can cryptographically erase information once it's been stolen. All right, so first, let me lock down some terminology. So I'm going to use the term PRF, which is short for pseudorandom function. But I'm going to say PRF because I'm lazy. Okay, so PRF is really simple. It's going to take an input, some arbitrary input. Imagine a document, or in our case is a password, and it may or may not take a secret key, right? And it's going to produce some fixed length output, and this output is going to be, for more or less, it's going to look like a random string, right? So think hash functions. In fact, hash functions are pseudorandom functions. So SHA-2, SHA-3, or keyed hash functions like HMAC. And when we're talking about passwords, things like bcrypt and scrypt, these things are all pseudorandom functions. So you take in some input, run them through some algorithm, you get some fixed length output. Okay, so let's talk about a motivating example. If you go to LinkedIn, the only way to access LinkedIn is you provide them an email address and a password. Now, of course, LinkedIn has to store this password in some way, so when you come back, they can check if your password is still the same. All right, so pop quiz. How was LinkedIn storing passwords in 2012? This is a multiple choice question. Someone in this room knows this answer. That'd be weird to do all the above. Okay, they weren't storing plain text password, thank goodness. Some people are, though. It turns out in 2012, they were storing unsalted hashes of passwords. Of course, the reason we know this is because in 2012, attackers broke in, they stole a large corpus of passwords, and then they leaked them online. And of course, once they leaked them online, because they were unsalted, security researchers had a field day. In 2 weeks worth of cracking, security researchers recovered most of the passwords. Now, the reason it was so efficient is because they weren't salting passwords. But I'd like to point out that even if LinkedIn was following industry best practices, if they were using salts and these iterated hashes that are harder to compute, this doesn't actually stop these offline dictionary attacks. It only slows them down. All right, it sounds like I'm picking on LinkedIn a little bit, but these password database breaches are common. Surely you guys read the internet, and occasionally on the internet we hear about these kinds of things. And these don't just happen to mom and pop shops. These are sophisticated technology companies. These are news companies. These are all kinds of companies who are experiencing these password database breaches. So our observation is that password database breaches are common. Now, of course, we want to limit these breaches from occurring if possible, but when they do occur, we want the data owners to have some recourse, and we don't want the recourse to be, sorry, your account has been locked. Also, probably your Instagram account has been also broken into because, I'm sorry, you used the same password everywhere, and now you have to log in and change your password. We want something better. All right, so let's look at a slightly better approach. In January 2015, Facebook presented this slide at Real World Crypto in London. So I'll talk you really briefly through it. This is how Facebook processes your password when you actually log in and type your password. So they take your plain text password, they run it through MD5. They then take a 20-byte they create a 20-byte salt. They run that through an HMAC with SHA-1. They then connect to a remote server, run that with HMAC SHA-2 on a secret held only on that server, send the result back, run that through ISCrypt, run that through HMAC SHA-2, and then store that in a database. Okay, everyone got that? Okay, so you're probably thinking, why is this so complicated, and why would Facebook do this way? The reason they do this way is actually historical. So let's walk through it one at a time. So once upon a time, Facebook had 800 million passwords that were MD5 hashes stored in a database. And they thought, rightly so, this is probably not a good idea. We should improve our strategy. But we have 800 million passwords in a database. It's unreasonable for us to say, hey, all Facebook users, log in on Tuesday, give us your password. We'd like to update our code and our database all in one day. So what do? So they want to move to a salted SHA-1 hash. So instead, what they decided to do is take the existing MD5 hashes, add a 20-byte salt, wrap them in SHA-1, and write them back to the database. A few years later, SHA-1 is broken, and they think, okay, now what are we going to do? Well, we're going to do the same thing. We're going to switch to SHA-2, in this case on another machine with a secret. A little bit later, they decide this isn't good enough yet, so they're going to add scrypt. Scrypt is kind of like a hard hash function, right? It takes a lot of computation to compute. So they add this to the existing database, but the scrypt output is really long, and they don't want to store that in a database, so then they run it through SHA-2 to make it smaller and put it back in the database. And what we're left with is this code. And this code is now an archaeological record of Facebook struggling with password storage technology. But I want to point out something really interesting. There's something here that most tech companies don't do. And that's this. At some point during processing your password, Facebook connects to a remote server, still owned by Facebook, but another machine, asks that machine to apply an HMAC SHA-2 with a secret that's held only on that machine, and then gets the result back. The reason this is interesting is this leads to a different kind of architecture. So architecture is more like this. So at a very high level, the user provides the password to the web server, which provides some of that pre-processing. At some point, it connects to this crypto server. The crypto server runs this HMAC SHA-2 with a secret and sends the result back. The reason this is nice is because now critical information is not only on one machine, it's now on two different machines. So if an attacker breaks in and he steals either the password database or the secret, but not both, the attacker now has insufficient information to crack those passwords. He needs to attack both machines to do it. Okay, so this is a nice architecture, but there are still some limitations. So people who do cryptography might say, oh, I see a secret. The first question I might ask is, how am I going to rotate that secret? The dirty little secret inside Facebook is they actually cannot change this secret. If they change the secret, they're going to eviscerate their entire database of whatever it is, 1.4 billion passwords at this point, right? So they're sort of stuck with this secret for life. Okay, so that's not so good. The second problem is if an attacker breaks in and steals the password database and has access to the crypto server, he can't run offline attacks. Okay, so that's good. But if the attacker has access to the crypto server, he might be able to run online attacks. And because of the way Facebook has set up the API, it's really difficult for the crypto server to tell the difference between a large volume of legitimate traffic of passwords for different user accounts and a bunch of guesses for the same user account, because every guess looks distinct in the way this crypto server API looks. Okay, so we like this architecture, but we want to fix these problems. All right, so for the rest of the talk, I'm going to leave behind the state of the art. I'm going to talk about our contribution to how we protect passwords. And we're going to sort of start with this architecture, and then we're going to fix those problems that we saw. Okay, so the crypto server is now going to be called a Pythia PRF server. And we're going to change the API in such a way that now the crypto server can detect online attacks. And when it detects online attacks, it can do something about it. And we also want to, when we do something about it, what we're talking about is probably rotating the secret. So we can recover from compromises, and even if we don't detect compromises, we can proactively rotate secrets. And when we rotate secrets, that'll give us cryptographic erasure, meaning we're going to invalidate stolen databases through this key rotation. And finally, what we want to build is not something just for big tech companies like Google and Facebook. We want to build as a multi-tenant service. We want to build something that a service provider can build it and allow players of all sizes to use this to protect their passwords and yet not have to outsource all their security. Like, I'll just give you all my passwords and hope that you don't get compromised. We want some better balance than that. Okay, so what I'd like to do for the next 3 minutes is take you through a high-level view of how Pythia PRF service works, and then I'll dive into some nitty-gritty details. Okay, so we'll start with, we have a web server. It's using Pythia to harden passwords. How does it enroll a new user? So the user logs in the normal way, provides a username and probably a really crappy password that's also used on a bunch of other websites. The web server is going to choose a random value. We'll call that T. This is going to be a user ID. And it's going to run the password through a blinding function. I'll define this later. We'll call that result X. The web server is going to connect to the Pythia server and issue a query. And the query is going to contain the following. It's going to have a value W. This is just a web server ID. It's going to have that user ID that we just established. And it's going to have this blinded password. So the Pythia server is going to look up in a key table, and it's going to fetch a key that's assigned specifically to this web server. It's then going to run the user ID and the blinded password through this function, this f sub k. And this is going to be our key PRF, and I'll define this in a little bit. And the result is y, and it's going to send the result back to the web server. The web server is then going to run an unblinding function, and it produces some value z. We call z a protected password. Think of it as, the output of an iterated hash or bcrypt or scrypt. And it's then going to write this to a database. It's going to write the username, the user ID, and this protected password. And then when the user logs on again later, the web server runs essentially the same protocol. It produces some new value z prime. When z prime equals z, the web server knows, this was the original password. And when it doesn't match, it just knows, no, that's not the right password. Okay, so that's enrolling a user and checking a password. Let's talk about compromise recovery. Okay, so web server has this big database of protected passwords. Bad guy breaks in, maybe he gets a SQL injection, he steals 7 million, or in the case of Yahoo, 2 billion, or not 2 billion, 1.5 billion passwords. So the nice thing is if you're using Pythia, the attacker can't immediately run offline attacks. But technically he's got all the same information, he could probably run online attacks. But here the API is different, right? The attacker has to specify the web server ID and the user ID, which makes it really easy for the Pythia server to see online attacks, right? Maybe you get 10 or 20 guesses on a single user account before the Pythia server realizes, like, oh, this is not right. You can't try 100 different passwords. And the Pythia server can do something about it. It can ban the IP, it can throttle accounts, it can lock accounts. Probably most importantly, it can send an alert to the admin that says, hey, we see suspicious activity using your web server ID. So he sends an alert to the web server. The admin realizes there's a problem. He cleans up the web server, probably patches his SQL injection, and then the web server contacts the Pythia server and says, hey, I need to run key rotation. So he produces a new key K prime. Pythia server then sends a compact update token, we'll call this delta, that's going to enable the admin to update his password database from the old key K to the new key K prime. Okay, and so the admin runs this process. He updates all his ZIs to ZI primes. And I want to note that the admin does all of this offline in the sense that he doesn't require user interaction. He doesn't ask his users to log in and change their password. He doesn't have to lock their accounts. He can do all of this himself. It doesn't need the original password, and the user's password doesn't change, actually. We're just updating the encryption to a new key. When he's done, he contacts the Pythia server and says, hey, the key, I'm done with key K, so I want it deleted. And at this point, when the Pythia server deletes it, we're now invalidating an old password database. Okay, so if there's any cryptographers in the audience, you may already be thinking about, like, what kind of primitives do we have? What kind of properties do we need to implement this? Okay, so let's go quickly through the list of requirements. So we need a scheme that's deterministic. Given the same user ID, key, and a password, of course we need to produce the same output. We need the output to be pseudorandom. And we need this weird property, this partial message privacy. We want to require users to specify the user ID in the clear to the Pythia server, but we want to hide the password, so if you break into a Pythia server, you don't actually see passwords. This is kind of a weird property. And now, of course, we need key rotation. This enables us to recover from compromises. Okay, so a bunch of schemes exist, at least in 2015 when we did this work. Pseudorandom functions, Oblivious pseudorandom functions, things called partially blind signatures. There's a couple other schemes that give us updatable encryption. But in 2015 when we did this work, if you looked at the intersection of all of these, it turns out there were no existing schemes. So we had to create a new scheme, something we call a partially oblivious pseudorandom function. Okay, so I'm tempted to go into serious details. There's only 2 slides of math, so for those of you who don't care about the details, it's only 2 slides. Hang with me for a little bit. Okay, so I'll tell you how we build our partially oblivious PRF. We build ours using something called a bilinear pairing, and that's a function E, which maps inputs from 2 groups onto a target group, and it has to satisfy this function. Maybe more importantly, each of these groups, we have something called the computational Diffie-Hellman assumption, meaning given A and X, it's easy to compute A and X, but if I give you the value A to the X, it's hard to get back either A or X. This is called discrete log hardness. Okay, so given such a bilinear pairing, this is how we build our scheme. This is the blinding function. We take the password, we hash it onto a group, and we raise it to the power of R, where R is just some random blinding factor. It's going to be selected uniquely for each query. This is going to perfectly hide the password so the Pythia server doesn't learn any information about passwords. Send this to the Pythia server, and then the Pythia server applies this keyed PRF. So we take the value X, we hash the value T, and we run it through the bilinear function, we raise the whole thing to the power K. And then the unblinding function is really simple. We take the inverse of R, and we raise the result to that. And if you write out what this looks like, you'll see that the blinding factor and the unblinding factor cancel out naturally. And what we're left with is a deterministic computation using the inputs we wanted precisely, so the password and the user ID, all raised to the power of some secret key K, and that secret key K is known only to the Pythia server. Okay, so that's enrolling a new user and verifying a password. Compromise recovery is really simple. So we send a fraction K prime over K. Doesn't leak any information about either key. Updates are really simple. You take this value, you raise it to the power of this update function. If you write out what that looks like, you'll see that the old key cancels out and only the new key is left. And so after an update function, we have the same user ID, same password, but now under a new key and no residue from the old key. Okay, so that was a really deep dive. Let's look at the big picture and let's talk about what all this buys us. So first off, we have a Pythia server that only sees blinded passwords, meaning it never sees the individual passwords. And it has enough information, meaning to detect online attacks, meaning that you have to provide correct web server IDs and user IDs in order to get the right answer. So it's going to be easy for a Pythia server to tell the difference between legitimate traffic and illegitimate traffic. On the web server side, the web server never learns the secret key. And this is really nice because if someone breaks in and they steal everything on your web server, you want them to be missing some information. Okay, so we built one of these things. Itself is open source. We built it using open source. It is just a prototype, but we built it using Nginx. We did the implementation in Python. Store the key table in Mongo. You can get the source code on GitHub. Check out my websites for information to find these things. There's even a test and development server, which I don't recommend for production because it could go away in any day. But you can build Pythia clients and you can use our server if you want to test your clients. So real quick, let's talk through some implementation or some evaluation details. Essentially, Pythia is fast and scalable. So if the Pythia server and the web server are on the same network, so there's essentially no network latency to worry about, we can do Pythia queries in 5.2 milliseconds, right? That might not mean anything without context, but to put this in context, if you do iterated hashing, if you follow NIST current guidelines of 10,000 iterations of SHA-256, that's going to take you, depends on the CPU and the implementation, but that's going to take you about 10 milliseconds, 9 milliseconds, right? So Pythia is going to be competitive with iterated hashing. And you get a very different security property. Actually, in practice, you can actually use iterated hashing and Pythia together. There's no reason you have to use one or the other. So throughput is good if you're hosting your own Pythia server. We can, on a single 8-core machine, we have a max throughput of a little over 1,300 queries per second. And storage on a Pythia server is excellent, right? So on the Pythia server, it only has to remember for each of its clients now are web servers, not users, right? So the Pythia server needs to remember a web server ID and a key. A little bit of extra information for detecting online attacks. But this is going to be independent of the number of users behind that web server. So to give an example, if I had 100 million web servers using a single Pythia server, the key table for that is less than 20 gigabytes, right? Independent of how many users are using those 100 million web servers, right? Each 100 million web server could itself have 100 million users, and still, I only need a 20 gigabyte SSD to store my key table. Of course, I should probably keep that key table very secure. Okay, so Pythia is fast and it's scalable. Today, I've mostly been talking about web servers, and that's because I think web servers are the most natural use for Pythia. In our Usenix paper, we talk about some more interesting ideas. One of the ideas we talk about is, really, you can use Pythia to secure anything that's using passwords in the sense of security, and you have an internet connection. So one of the things we talk about in the paper is called a Bitcoin brain wallet. And the idea here is that you have a Bitcoin wallet, you don't want to store the key somewhere. So you create some passphrase or some complex password. And then in the past, people would try to run these passphrases through an iterated hashing function, use that output to be your Bitcoin private key. Of course, the problem is if somebody cracks your password in the same way, then they now own your Bitcoin wallet. So you can imagine doing the same Pythia work. You take a password, but instead of running it through iterated hashing, you connect to a Pythia server. You run this blinded protocol. You get some result and use that result as your Bitcoin private key. And then when you want to update your Bitcoin wallet, you actually don't even have to change your passphrase. You just connect with the Pythia server and have it rotate its key periodically, and you transfer funds from one wallet to the next. So that's a fun idea. And the other very straightforward idea is you can imagine doing file encryption this way, right? So it would require an internet connection, but you can imagine you put data on a remote hard drive or on a laptop or a phone, and you want to encrypt that data with a passphrase, but you want to use Pythia to harden that password. And the nice thing is, if you lose that device and you want to erase that data, you don't have to wait for that device to come online. If you have access to the Pythia server, you go to the Pythia server and you say, hey, I want you to delete this key. And when it deletes that key, it's going to erase this device, whether or not that device is online, right? So this is a very nice property. Okay, so what is the takeaway from all of this? I claim password storage is broken. Password databases get breached, and when they do get breached, it's too easy to crack passwords. We can fix this. We fix this using Pythia, which not only prevents offline attacks, but it enables us to detect online attacks. And when we detect online attacks, we can do something about it. We can rotate keys. That allows us to cryptographically erase old information and then continue operating forward. And finally, because we're using a service architecture, the idea is that this should be accessible to more than just people with lots of technical infrastructure. This should be enabling people of if you have some service providers providing Pythia services, you can imagine a whole range of people with different technical sophistication being able to gain the power of this strong cryptography. And with that, thank you for your time, and I would love to hear your questions. Do I have a link to the white paper? You can find it. Let's see if I can find this slide. You can find it on my webpage. If you search Google for Pythia PRF, there's probably not too many different responses. This is too slow. Let's see. Yeah, there we go. Yeah, so this is my webpage, and you can find the paper from here. Pythia, see if I remember this correctly. It's been a while since we named this. So Pythia is the name it's the name of the oracle at Delphi, right? So it's supposed to be this kind of random oracle, right? You ask an inscrutable question, you get an inscrutable answer. Unfortunately, it's a very heavily used name, so there's a lot of Pythias in the world. Yeah. Yeah, so let me repeat the question. So the question was, this seems nice and tailored to a business setting. Is this going to work for the everyday person? I hope so. This is our plan. Actually, when we started this, what we wanted to do was protect passwords on the user side, and able to protect particularly like my Safari database of local passwords. Sadly, we got sidetracked and we ran off onto this other problem. I think so, but of course somebody has to be supporting this key server. So you can imagine if Google or Amazon or even 1Password were running their own Pythia server, and then individual people had software that used those services, it does seem feasible. Of course, somebody has to stand those things up and operate them. Yeah, question? How is the best attack relative to brute force? So we're using provable security here, and so the strength of security we get here is, sort of no less than you're going to get from the elliptic curves that you're using underneath it, if that makes any sense. So this is a very astute question. Okay, so let's see if I can find a slide to demonstrate this. Okay, so if I understand the question, it was if you trick the server, if you trick the Pythia server into running a key rotation, essentially, is this going to create a denial server on the web server? And the answer is, of course, absolutely, right? Which is a huge problem, right? So the thought here is that you use one level of authentication to verify queries, and then you need obviously a much stronger level of authentication to be able to do things like fetch keys, destroy old keys, that kind of thing. And the hope is that's a little more laborious to do that work, but you only have to do it periodically. Yeah, I mean, this is cryptographic erasure, right? Like if I break in and I delete the key and that's the key you needed, yeah, you're in trouble. But so it's a different problem because the keys are smaller, right? You can imagine the attacker breaks in and erases your database of passwords. You're also in trouble unless you have backups, right? So it depends. Yes, now the Pythia server is like outside of your data center, and now you have to deal with, is this other person being protected as well? So yeah, there are problems here. Yeah. Any other questions? Oh, yeah.
So this sounds like a really great application of the implementation into one of AWS's services or something like that. Do you have any, and actually personally it sounds like an excellent way to implement more trustless password management attack. Do you have any plans to build any kind of management?
Yeah, so I can repeat the question. This seems form fit for people like AWS and Google Cloud Platform to be building these service providers. And yes, we think that's absolutely true. Do I have any plans to do so? I do not, unless the right number of investors happen to be in this room, in which case I do. There is a group at Cornell Tech who's working on this thing. It's not clear how successful they'll be. Although I should say that software is not patented. The software is open source. If you guys want to stand up your own services, you're more than welcome to. And actually will be happy to volunteer to help with technical expertise to get these things off the ground. But yeah, this is our dream, is that if you're a AWS provider, you don't have to store passwords yourself, or you don't have to do all the work in password stuff. You can just subscribe to AWS's Pythia service, and then you can harden passwords as well. If you're running a Pythia server, yeah, of course you can, well, any curve is too strong. So our construction is based on a bilinear pairing, and so there's only certain sets of curves that work this way. Since we did this work, there's been a little bit more work that doesn't necessarily have to use that, so you have a little more flexibility in curves. But if you use our particular construction, you're stuck with curves that are compatible to bilinear pairings. But beyond that, yeah, you can use whatever curves that you implement. All right, guys. Thanks for your time.